Since Datagen is a key component of many LDBC workloads, so I will take the opportunity to give details what happens under the hood of the generation process. So I guess that most of you don't know how everything works and how things are generated, especially that the audience is rather new. Why a synthetic graph generator? The first motivation is that real graphs are difficult to obtain, either because it's not practical to get them out of the internet, or maybe because of privacy concerns. Companies are reluctant to give this data to people because they think it's a very valuable asset as well. So and also because this data is do not always have the required characteristics. It's ideally in a benchmarking setting, we would like to have a way to change the graph, to scale up the graph by changing the least characteristics, because otherwise you change a graph that is at a given scale, but then the distribution is completely different, or other properties are completely different, so the results are difficult to understand. So the wish list of a data generator, especially from the perspective of LDBC, is scalability, because as Alex said, we want to test very, very large systems, distributed systems, but also smaller ones that could even fit in a smartphone. So we want a data generator that can scale from a few gigabytes to terabytes of data. We want it to be realistic in terms of attribute distributions, but also distributions of the graph. We want induce correlations between attributes, not only attributes within the same entity. So, for instance, a country the name of a person is correlated with its country, or the interest as well with its country, but also between connected entities. So it's likely that I'm your friend and we have common interests. So we want to induce these properties, and also the structural characteristics that you will find in a real network, like a community structure or a large clustering coefficient, distributed and skewed degree distribution, a large connected component, diameter, so on and so forth. So, and finally, we want flexibility, because this allows us to say, okay, let's generate a graph at a given scale, and then let's try to change some of these properties and see how these affect the performance. So we can say this system runs particularly well when you have degree distributions that is not so skewed, or where the community structure of the graph is not so well defined. It allows us to apply a systematic way of benchmarking and knowing better our system. So for the reason, during the LDBC project, when it was an EU-funded project, and now we developed Datagen, which is a fork of the SG2 graph generator, which you can find here. So it's as Larry said before, it's open source. You can download it and play with it. Even you can suggest modifications and even pull requests. So if someone wants to contribute, I will be appreciated. So what does the Datagen generate? It generates similar to Facebook. It uses dictionaries from real data, specifically from the DBpedia, to assign real names to countries, persons, companies, topics, also to know the correlations between some of the attributes. As I said, the graph has correlated attributes. There's a correlated friendship subgraph, so similar people tend to be connected, so people with similar attributes tend to be connected. It supports realistic distribution, so what we did was to model or to empirically reproduce the distribution found at Facebook, but you can also provide your own degree distribution if you wish. And also, we generate the activity of the persons in the social network, messages, posts, replies to messages, likes, whatever. And we try to make this activity not uniform across the timeline where we simulate the network, but to have spikes as you would find in real world when some unexpected event occurs, like elections or sports events or whatever. This is the schema. We have person. I think that cannot be read much, but basically persons have creation date, first, last name, gender, country, interests, emails, the language they speak, many information. Also, we have the messages as well with the creation date, the IP where the message was created, the browser, the language, the content, also the topic the message is talking about, blah, 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 basically. The good thing is that the schema is rather complex, so this allows us to, especially in the case of the SNB interactive and BI workload, to create a wide variety of different queries that stress the data set and the systems in different ways. It's built on top of Hadoop, because this allows us to generate huge amounts of data in a scalable way, and it is deterministic. So regardless of the machine you use and the amount of computing nodes you have, the data set will be the same as long as you configure it with the same configuration parameters. So you have probably already seen this slide. It was in the Alex presentation with different color. This is the execution process of Datagen. We start first with the data generation. With the person generation process. Then we generate the friendship subgraph. Then we serialize this friendship subgraph, because in case of graph analytics, we only need the first three boxes so far. We will see in the future. And then if we need the activity of the person, so the messages they created in the social network, which is required for the SNB interactive and BI workloads, we execute these two steps. So I start with this part. So I will basically run an example where we have four machine cluster with 100,000 person network we want to generate, and with a parameter which is a block size of 10,000. So we can divide these persons in blocks of 10,000 persons. So first phase, in the person generation, what we do in Hadoop is to basically execute a map operation. So each computing node will be responsible of generating a block of persons. And as a result of this process, we create a Hadoop file. Every time you see an elephant, I mean it's a file. So, in this case, this file is a Hadoop file. You know Hadoop files usually have a key and a value, where we have the person ID and the value of the person. And the value of the person actually is a serialized Java object that contains all the person's information. The important thing is that each block has its own independent state, which consists of a set of random number generations, degree sequence generations, and which are seeded by a specific seed that depends on the block ID, and the set of dictionaries. And we generate the block of persons, which are serialized in the HDFS file. Wow. Yeah. So once we have the persons, we start by adding connections between these persons, which is the nose graph generation, which is actually subdivided in three edge generation sub-steps. Each of them tries to create edges based on what we call a correlation dimension. As I said, connected people in the produced graph have correlated attributes. So one correlation dimension is the interest of that people. So people with similar interests are more likely to be connected among them. Another correlation dimension is a key composed by the university, the age, and the gender. So people that studied in the same university have similar age and gender are more likely to be connected. And finally, we have a random key to basically to reproduce the randomness of some edges that could appear in the graph. So for each of these correlation dimensions, we have an edge generation substep, which consists of the following. Remember that we have the person file, whose key is the ID and the value of the person. The first thing we do is to parallel sort and run this person file and sort by the corresponding correlation dimension, namely the interest. And then we rank the persons in the order they appear in the sorted array. So the output of this first phase is a new persons, new Hadoop file, whose key is and the value of the person. And we use this run to partition the persons into the blocks, usually using a conventional modulo partitioner. So then, for each of these blocks, which again have their own independent state, seeded with an ID that depends on the block ID, we have the array of persons, and we start throwing edges from each person to the persons in front of it, in a way that the probability of creating a person decreases geometrically with the distance we have in the array. So the farther they are, the less likely will be to be connected. There is a minimum probability, I think, of 0.2 to be connected, because otherwise it decreases very fast. But the key point is here. Closer people in the array have a higher probability to be connected. And also, know that this induces the formation of triangles, because these people will be more likely to be connected among them. So this is what makes our resulting graph to have a larger number of triangles than that you would be expecting in a random network. Of course, each person has a degree assigned that came from the previous step. So we create an edge if and only if there is room for a new edge to be created with this person, between these persons. When we create an edge, we assign the timestamp of that edge, but we also assign a weight to this edge. And this weight can be computed by a function provided by the user. So you can customize the weight you assign to the edges you create. And this is, I'm especially emphasizing this point because this design decision actually incurs in an issue into the data generator, because it means that all the data of the persons must be available in case someone wants to use this data to generate a weight that depends on this data. And later we will see why this is important. So once we have created the edges, we serialize the edges in this person edge file, which basically contains the person with the edges attached. Finally, when we have done 3 executions of this edge substep generation phase, what we do is to merge the files in order to remove duplicates. In practice, the number of conflicts is, what I have seen, it's for the first presentation or for the 2? Oh, sorry. In practice, we detect about 1-2% of conflicts between edges, at least with the distributions we have played with. So it's not a big issue. So activity generation. It works similarly in the sense of like how we generate edges. We first need to split the persons into blocks. In this case, the key we use to split these persons into blocks is the same random dimension, correlation dimension. How we generate the activity? There are two ways of generating activity. One which we call the spiky activity generation, and the other is the uniform. For each person, we generate each wall of the social network, generate its members. In the case of the wall, the members are the friends of that person. So this is important as well, because it means that when we create the edges, we need to attach to the edge some information about the friends, because the information needs to be used later in the activity generation. So this is another issue with this way of generating data. And finally, when we have the members, what we do is to create these cascades of threads and replies in a way that you create a set of posts, then for each post you create replies, and then keep for each member creating messages that can reply to these posts in a way that you create this cascade. And finally, also for each person, we create groups, which are basically forums in the social network that are where that person is a moderator. And similarly, we create members. We add members. In this case, the members can be either the friends of the persons, but also random persons. And this is the reason why we sorted the persons randomly in this step, to get random persons that fall within the same block. So, and again, we create the cascades. In the case of the uniform, both Spike and uniform follow the same skeleton, but in the case of the uniform, the topic of the initiator, the topic of the post that initiates the cascade is correlated with the topic of the interest of the person, of the creator, and the creation date is selected uniformly between the date that the person created the profile in the social network, or the max of this profile creation date, or the parent, the message parent, in case if this message is a reply of a post until the end of the simulation time. In the case of the spiky activity generation, what we do is first we create a set of flash mob topics that span all the timeline with different volumes of activity, which basically represent how important is this event in the real world. Then, given the person creation date, we create a random, we select a random flash mob post to its volume. So they are not uniformly selected, but they are proportionally. So the most popular are more likely to have a message talking about this topic. And then we use the time of this and the topic of this flash mob tag to select the topic and the time of the creation of the message around following this shape around this message. So all the features that are present control the size of the graph, which can be person-based. Now we are adding a new feature where you can directly specify the number of edges you want the resulting graph to have instead of the number of nodes. We can generate only the friendship graph without all the activity. This is especially useful for the Graphalytics benchmark. And you can customize things, edge weights, how the degree distribution of the graph, other internal parameters, realizers, even the way we create edges, you can customize it and override this. The way you create the text that are in the messages, also I said data, I wanted to say date formatting as well. So basically, conclusions, Datagen allows us to generate a realistic social network based on a map-reduce approach. In the case of Graphalytics, where we only generate the graph, so far we have been able to generate 30 billion edge graph, but by putting more machines, we could go even further. The only I would say drawback of this generator is currently is its monolithic execution model. So things are generated even if they are not needed, because for some workload they need something at a later step that might require this information. Okay, in the case of Graphalytics, we are generating a lot of attributes for persons, but in the end we just need some data that is computed based on country and the graph structure. We don't need the persons, but we pay the price. So this hinders scalability. And what we are not going to do is to have a different execution path per workload, because then it makes it unmaintainable. So, as I said, this leads to bad use of resources. So, in Datagen 2, which is what we are working on, It's a completely new data generator with a new architecture execution model. That what we will do is to use in-place data generation, like Myriad does, where it avoids sending information around, but generates information based on a seed. We just send the seed and generate the information. And language-driven, in the sense that users will be able to explain, to specify the schema, and the system will be smart in such a way that it will schedule the generation process and that generate the data that it requires at a given moment. So thank you, and we are recruiting in the sense that if you want to contribute and help me with this, this will be appreciated. While I switch the presentation, you can start doing questions.
Thanks, Arnau. What kind of questions do we have for Datagen? In the meantime, while you're thinking, I mean, you say that you want to do in-place data generation.
Yeah.
But for some kinds of scalable generation, you would need to communicate.
Of course, of course.
Or to send data around.
Exactly.
So is this really tenable for?
I mean, the thing is that why do you have to pay a cost if you don't need to? I mean, I want a system that if the user says, I want to generate this, it can optimize the generation process and say, for this particular scheme you want to generate, you don't need any transfer and generate this. But also, if in some situations you need to set some state that must be shared across different nodes, then the system will decide to do this. It's like
okay, so only when needed.
Exactly.
Because I mean, the edge generation with this window of blocks. I mean, it is like that. I think because some of the characteristics of the persons you're pointing to are taken into account to decide whether there is going to be an edge or not. So if you would not need any information about the person you are making a friendship with, then you could do in-place generation without worrying. But if you need, because you need to consult properties and characteristics of the remote person, then you start, and you cannot really assume this
but you can
all in the same machine in the same memory.
Exactly.
Then you start moving into
but in that case, you can still use in-place generation in the sense that you only need the seed, which is much cheaper than sending the full persons.
Not because, for instance, that we have to. I mean, I'm not sure what kind of restrictions are there now, but for instance, that suppose that you're trying to maintain some constraints, like you want a person not to have more than a particular amount of friendships. Okay, so the remote person you're trying to connect with needs to meet that constraint. So you somehow need some information of that remote person in order to ensure that.
Exactly.
Or in our case, yeah, you want to make sure that they have maybe some value in common. You know, they went to the same university. This is not maybe the case right now, but only if you have a generator that takes no information into account of the remote person, then you can do fully in-place generation. If you need information, then somehow this breaks.
I mean, I think that your point is there are many constraints that you could think of.
If you
want
to generate all this correlated stuff.
Yes, but I mean, you could even say, okay, you could establish relations between attributes, so one attribute is greater than another. You can think of many constraints, like for instance, that the distribution of observing to given attribute values of connecting people follows certain distributions, whatever. In the end, what we are trying to do now is to define exactly how far we want to go, okay, which is the minimum set of things we want to be able to model, which for me are these ones. Okay, you could even think of more, but for me, the minimum thing schema and the properties, the minimum constraints we should be able to generate are these. And for some of these constraints, as you said, you need some sort of a state that must be shared. Okay?
Okay, other questions? Okay. That's one question.
Like you are making a lot of assumptions about the data, and like you validate it, you periodically validate it somehow with I don't know, some system graphs.
Okay. Okay. What we do is to basically to check that the results we obtain, the data set we obtain, and the characteristics are those that we wanted. In the end, we want a clustering coefficient that it's close to that you would observe in Facebook, because in the end we are based on Facebook or a social network like Facebook. We validate that we have a large connected component. We validate that the distribution is that we specify. So these are the things we validate. Okay?
So you have a set of measurements and then you just check against.
Yeah. And also some tests to test that some constraints are fulfilled.
There is a great paper of a few years back that analyzes and compares SNB
Yeah.
output with realistic data.
In terms of community structure.
Community structure.
Okay.
Thank you.
Okay, so I start.